Hi, welcome to our poster for the class CS236 Deep Generative Network at Stanford. This is the title of our project, Towards More Accurate and Generalizable Brain Deformation Estimators for Traumatic Brain Injury Detection with Domain Adaptation based on GAN. Here, we will walk through the story of how a generative network model can be used to solve a generalizability problem in the specific application of brain injury detection and why this is important. As you can imagine, traumatic brain injury can happen in many common scenarios, such as during a car crash or certain sports accidents. Sometimes this could result in very severe damage to the central nervous system or even death. For the purpose of research and clinical treatment of brain injury, we need to learn how forces can result in brain damage in a quantitative manner. So how do we do that? From basic mechanics, we know that a head impact causes deformation across the brain, which can be characterized by two physical quantities, namely the strain and the strain rate. In experiments and simulation, people try to use force signals collected from sensors to predict the strain and strain rate. And one of the state-of-the-art approaches is using deep learning models, which will give us a deformation estimator, as mentioned in the project title. However, the sizes of data collected from real head impact events or on-field data are extremely small. As one can imagine, these data are valuable but very hard to acquire. Thus, most current deep learning models will instead trained on simulated impact data, which is much more accessible. And here comes the generalizability issue. These models do not perform well in predicting the deformation of the on-field impact event. Or in other words, the current models have difficulty generalizing to other datasets, including the on-field data we care most about. In this project, we try to solve the problem by performing the task of domain adaptation using a GAN architecture to firstly map the on-field data to the domain of the simulated data before feeding them into the estimator for prediction. Here, we are essentially transferring the styles of different types of head impacts. In the method section of this poster, we divide the project into three goals. First, we train a GAN for domain adaptation, which can map the on-field data to the domain simulated data, or the other way around. Second, a set of DNN models is trained on simulated data to take sensor signals as input and to predict strain and strain rate as output. Finally, we combine the GAN model and the DNN prediction models into pipeline and test the effectiveness of our method compared with the baseline method. Specifically, the GAN architecture is shown in the schematic. There is a pair of generators to map data between two datasets, and a pair of discriminators that try to tell apart mapped data from the original data. The most important reason to pick GAN as a model of choice is that we can enforce the property of cycle consistency by minimizing the reconstruction loss, which is the difference between the original data and the data mapped to the other domain and then back again. This makes sure that we do not lose the physics of impact during domain adaptation. The dataset we use for this project includes the largest head model simulated impacts with over 12,000 impacts, the college football impacts, the mixed martial arts impacts, the National Football League impacts, and the Nizza car crash impacts. The methods with which we compared the GAN-based approach against are firstly the baseline method, where we train the maximum principal strain and maximum principal strain rate prediction models on the head model simulated impacts, and then directly use them to predict the strain and strain rate of the on-field impact. Secondly, we compare the GAN-based approach with the convex optimization-based domain adaptation method named domain regularized component analysis.
And here comes the result. Firstly, we can see from the first plot on the left of the third column that the reconstruction loss, which dominates the total loss, steadily decreases with the training epochs. In the second subplot on the right, we have shown the accuracy of the discriminator for the real and fake head models data, the real and fake mixed martial art data. We could see that the discriminators successfully classify the real data, while the accuracy for the generated data oscillates with the adversarial training of the generators and discriminators. Our goal is to do the MPS and MPSL prediction. The result here following the two subplots show that after performing domain adaptation, the accuracy could generally be improved when compared with the models trained without any domain adaptation. The bi-GAN approach generally improves the accuracy and performs similarly to the convex optimization-based domain regularized component analysis, the DRCA. And on the top of the bi-GAN, we added the kernel means matching, the KMN, and DRCA to further address the potential distributional drift after data generation. And the accuracy is also like DRCA and better than the baseline. One exception is in the result is in the National Football League dataset. We believe this is caused by two reasons. Firstly, the NFL dataset only includes 36 impacts, which may be too few to sufficiently represent the true data distribution. And secondly, the NFL dataset and the head model simulated impacts may bear high resemblance because the head model simulation is designed to generate the NFL football-like impacts. To sum up, the bi-GAN-based domain adaptation resulted in substantial improvement in deformation prediction accuracy for different types of on-field impact data compared with the baseline and performed similarly as the convex optimization-based DRCA method, outlining the importance of domain adaptation before predicting the MPS and MPSR. We resolved the generalizability issue of deep learning models on the hard-to-obtain on-field data to a reasonable extent and allowing for more accurate estimation of brain injury in clinical and academic circumstances. That's all of the presentation. Thank you very much for the privilege of your time.